I am Sridhar Chitta. In a set of two videos, I shall discuss the basic action of a differential amplifier, which is the heart of the operational amplifier, using a unified approach to electrostatics and circuits. I express my sincere thanks to Professor V. Kamaraju, retired principal and professor of JNTU College of Engineering, for his expert comments, which helped me structure the flow of ideas beginning from differential and common mode currents to an introduction of the principle of the differential amplifier in this video, part 1 of 2. I shall begin this video, part 1, by describing differential mode and common mode currents and the origin of common mode currents. This is followed by a description of the principle of a U-Tube Manometer whose action is analogous with that of a differential amplifier. Finally, I shall discuss the principle of the operational amplifier and introduce the differential amplifier, which is the first stage of an integrated operational amplifier. And in the video of part 2, after introduction in continuation from part 1 of the description of the operation of a differential amplifier, I describe the physical aspects of the differential mode and common mode action and a demonstration of the rejection of common mode signals. Then, a discussion of the electric field components in the amplifier is followed by enhancements to the basic structure of the amplifier, which makes it suppress common mode output voltages. The animations in the video are useful as an aid to visualize the circuit processes in the operation of the differential amplifier. We have not shown the surface charges that are present, which enable the conduction processes in the components for the sake of clarity. It is recommended that the viewer refer to the two videos 1 and 2 listed in the references at the end of this video, which provide a comprehensive description of the role of surface charges in enabling conduction in electrical and electronic circuits. Engineers are so used to thinking and visualizing currents as differential mode in circuit analysis that they find it hard to switch their thinking to common mode currents and their effects in, say, amplifying circuits. We will begin by visualizing differential mode current in transmission line cables and then discuss the origin of common mode currents in these cables. The electrons drift from the negative terminal to the positive terminal everywhere in the wire. This is the differential mode component of the total current. The direction of electron drift during the positive cycle of a sinusoidal voltage will be the same if the battery is replaced by a sinusoidal signal source. Now we will visualize the common mode component of the total current in the transmission line cables. The electrons in the right wire drift from the right of cross-section point A to the voltage source. Electrons in the left wire drift from the left of point A to the voltage source. This is the common mode component of the total current. Generally, both differential mode currents IDM and common mode currents ICM are present on a two-wire transmission line shown with terminations of an internal source resistor and a load resistor. Transmission line theory and the transverse electric mode or TEM assumption applies only to the differential mode currents on the line. The differential mode currents IDM on the two conductors are, by definition, equal in magnitude and opposite in direction at any cross-section in the line. The term differential mode is also referred to as transmission line mode, normal mode, metallic mode, bidirectional mode, and odd mode. The common mode current is that which, flowing in each conductor, is equal in magnitude and directed in the same direction, according to a definition made by Clayton Paul. Common mode currents produce erroneous measurements made by operational amplifiers. Let us visualize the differential mode current in twin lead cables. The upper figure shows an antenna to TV twin lead cable. The lower figure shows the electric E and magnetic B fields at one instant of time when the twin lead cable is excited by a radio frequency signal generator. The current is differential mode since it is equal in magnitude and opposite in direction. The orientation of fields between the two wires shown in the dashed transverse electromagnetic or TEM boundary resembles the orientation of the transverse electric and magnetic fields in a perfectly conducting parallel plane transmission line. We will now study the origin of the common mode component of current in twin lead cables. The two leads of the TV twin lead cable being closely spaced, a common mode of current flow may exist, that is, the currents of both conductors flow in the same direction. Applying Lenz's rule to the right-hand wire, assuming that the current in the left-hand wire is increasing, you will find that the associated Coulomb field in the right-hand wire also points into the page, making the current into the page. The current is therefore common mode. For a description of Lenz's rule, refer textbooks 3 and 4 listed in the references at the end of this video. The common mode current will make the magnetic field B1 appear for certain combinations of frequency, line parameters, and geometry along with the field B of the TEM mode, and in special cases when the TEM mode is completely blocked. Such a process is termed differential to common mode conversion. We will visualize the differential mode component of current in coaxial cables now. Coaxial cables are used to connect home video equipment, in ham radio setups, in measurement electronics, and in broadband internet access through modems. The energy conveyed by the electric and magnetic fields is guided along the line by confining the electromagnetic wave to regions between the inner and outer conductors of coaxial cables. A current of plus I amperes will be carried in the inner conductor and a current of minus I amperes in the outer conductor. There is a penetration of the fields in the conductors as well. The mode of propagation is essentially transverse electromagnetic or TEM. The current is differential mode. We will now study the origin of the common mode component of current in coaxial cables. It may seem that the coaxial line offers simplicity in supporting perfect TEM mode propagation. However, leakage of the input signal through the shield, remembering that a magnetic field penetrates through matter, supports common mode currents on the outer surface of the shield. The direction of common mode current on the shield may be verified by drawing the magnetic field lines B outside the cable and applying the right-hand rule for current. The current will be in the same direction as the center conductor, that is plus I. Such a process is termed differential to common mode conversion. We discussed one among two processes which may cause the appearance of common mode currents in the twin lead and coaxial cables, referred to as differential mode to common mode conversion. The The term common mode is also referred to as antenna mode, dipole mode, longitudinal mode, and even mode. Only the differential mode current flows in the terminating impedances. The conventional common mode current is zero at both ends of the line. The second process by which both common mode currents and differential mode currents appear on transmission lines is when they are induced by external magnetic fields. A comprehensive description of the source, nature, and characteristics of differential and common mode currents is available in textbook 5 listed in the references at the end of this video. An intuitive understanding of the operation of operational amplifiers can be gained by studying the analogous operation of a U-Tube manometer, which is used to measure pressure differentials across a boundary or a barrier in the flow path of fluids and air. We will learn in this presentation that the basic function of an operational amplifier is performed by the input differential amplifier stage, whose operation is similar in some respects to that of a U-Tube manometer. The manometer consists of a glass-walled U-shaped tube filled with a liquid such as colored water to measure small differential pressures of the order of a fraction of atmospheric pressure. The low density of water makes it suitable to measure pressure differentials which are expressed in inches of water. When the air pressure is equal in the open ends, the water level is the same in both the limbs. Now let us see what happens when the pressure is different in the two limbs. The air pressure increases above atmosphere in the left tube. The air pressure increases above atmosphere in the right tube. The U-Tube manometer is used to measure the difference in pressure around bends and across filters in cooling coil units in air ducts of large air conditioning systems which cool rooms in hotels and office spaces in commercial complexes. Large air conditioning systems generally cool large quantities of water in chillers located conveniently in basements or rooftops to prevent nuisance from noise due to operation of large refrigerant compressors in the chillers. The chilled water is circulated in rooms and office spaces and flows in cooling coils placed in air ducts. A blower fitted to an air handling unit blows air over the cooling coils, and the duct directs the cool air into rooms and office spaces. The measurement of the static differential pressure of air across bends and filters in cooling coil units is made by placing the tips of tubing from the two ends of the U-Tube manometer upstream and downstream of filters. The pressure readings are monitored by maintenance teams to detect a fall in air supply and take appropriate remedial action. Is used to screen particles of dust from entering a room cooled by air flowing over a cooling coil, and the filter over course of time will become dirty. There will be a change in static pressure across it, which can be monitored by a U-Tube manometer. When the filter becomes dirty, the static pressure differential, which is the upstream pressure minus the downstream pressure, increases. While the principle of the U-Tube manometer seems simple, the cause of certain errors in pressure measurements should be noted. This will make it easier to appreciate the development of the scheme for the differential amplifier in the video of part 2 of 2. These are when absolute pressure calculations are made with atmospheric pressure as a reference. When one limb is exposed to the atmosphere, errors will result if the atmospheric pressure were to change. The manometer measures the difference in pressure in the two limbs, and its reference level should not be allowed to change if the pressures are the same, whatever be their intensity. The total length of the column of water in the two limbs should not be allowed to change when differential pressure measurements are being made. Small differential mode signals can be represented by two sine waves which are 180 degrees apart in phase. Sensor signals are sums of a pair of sine waves 180 degrees apart. Instantaneous values of varying components of signals at the two terminals are represented by Vs1 and Vs2. Graphically, this value is shown by a line above and below the signal 0 against time. The viewer should note that a sinusoidal voltage generator operates by separating charges for the positive half cycle in one direction initially rapidly and slowing down and momentarily halting when its voltage is at the positive peak, and then gradually reuniting the separated charges to make the separation zero. When all charges reunite, the generator voltage is zero. The process repeats in the reverse direction during the negative half cycle. Refer the textbook 4 listed in the references at the end of this video. The signals of interest from the sensors such as thermocouples and sensor electrodes in medical electronics are generated by separating unlike charges and are differential mode signals. The received weak signals of the order of microvolts from sensors could be noisy due to interference from external signals. Noise, an unwanted effect, affects both the wires connected between the sensor and the receiving amplifier. Noise causes the potential across the two wires to rise or fall at the same time at the same point, a common mode signal. The function of the differential amplifier is to amplify the difference between two signals. The need for differential amplifiers arises in many physical measurements where response from DC to many megahertz is required. It is also the basic stage of an integrated operational amplifier with differential inputs. The figure represents a linear active device with two input signals V1 and V2 and one output signal VO, each measured with respect to ground. In an ideal differential amplifier, the output signal should be given by VO minus AD multiplied by V1 minus V2, where AD is the gain of the differential amplifier. It is seen that any signal which is common to both inputs will have no effect on the output voltage. However, a practical differential amplifier cannot be described by the expression because in general the output depends not only upon the difference signal Vd of the two signals but also upon the average level called the common mode signal Vc, where Vd is identical to V1 minus V2 and Vc is identical to half of V1 plus V2. For example, if one signal is plus 50 microvolts and the second is minus 50 microvolts, the output will not exactly be the same as if V1 is equal to 1050 microvolts and V2 is equal to 950 microvolts, even though the difference Vd, which is equal to 100 microvolts, is the same in the two cases. We will now introduce a figure of merit for a differential amplifier called the common mode rejection ratio, or CMRR in short. The output V output or VO can be expressed as VO equals A1 multiplied by V1 plus A2 multiplied by V2, where A1 is the voltage amplification from input 1 to the output under the condition that input 1 is grounded, and similarly we can define A2, the amplification between input 2 and the output. From equation 2, V1 is equal to Vc plus 1 half Vd and V2 is equal to Vc minus 1 half Vd. If these equations are substituted in equation 3, we obtain VO is equal to AD multiplied by VD plus AC multiplied by VC, where AD is equal to 1 half A1 minus A2 and AC is equal to A1 plus A2. We can measure AD by setting V1 equal to minus V2 equal to 0.5 volts, so that Vd is equal to 1 volt and Vc is equal to 0, and the measured output signal VO gives the gain AD for the differential signal according to equation 4. Similarly, if we set V1 equal to V2 equal to 1 volt, Vd is equal to 0 and Vc equal to 1 volt and V0 is equal to AC. The output voltage now is a direct measurement of the common mode gain AC. We would like to have the differential mode gain AD large, whereas ideally the common mode gain AC should equal 0. A quantity called the common mode rejection ratio, which serves as a figure of merit for a differential amplifier, is defined by CMRR equal to ρ is equal to the absolute value of AD and AC. From equations 5 and 7, we obtain an expression for the output in the following form. V output equals the product AD-VD multiplied by 1 plus 1 over ρ multiplied by Vc divided by Vd. From this equation, we see that the amplifier should be designed so that ρ, that is the CMRR, is large compared to the ratio of the common mode signal to the differential signal. Let us attempt to develop a circuit scheme for a differential amplifier, sometimes called difference amplifier, applying ideas that we learned from the study of the operation of the U-Tube Manometer. Note that the circuit should preferably amplify only differential signals, including DC or slowly varying signals, and not common mode signals. We begin by constructing a circuit using two NPN transistors with identical characteristics and two resistors. Surface charges and interface charges are not shown in the following figures because of their complex arrangement, but these are present, and it is these charges that set up driving electric fields within conductors, resistors, and transistors. The circuit we will show uses two NPN transistors with identical characteristics with their collectors connected to two identical resistors RC. A power supply rail plus VCC is then added, and the two emitters of the transistors are joined. The attempt is to create a circuit which will mimic the action of the U-Tube Manometer. The signal voltage or EMF is between two input wires and is applied to the base terminals. Their instantaneous varying voltages are labeled Vs1 and Vs2. The output voltage is between the collectors of the two transistors, and these are labeled VO1 and VO2. If all goes well, we should obtain an output voltage V output 1 minus V output 2 at the collectors proportional to the difference of the input signal voltages Vs1 and Vs2, as if the circuit of the differential amplifier scheme 1 mimics the operation of the U-Tube Manometer. In the manometer, the difference in lengths of liquid in the two limbs is proportional to a differential pressure over the liquid column in the limbs. Circuit analysts, on inspection of the circuit topology scheme 1 will say it won't work. Note that no point of the circuit is returned to the negative of the power supply voltage. Shown connected is only the positive terminal of the power supply plus VCC. Therefore, under any condition of the differential or common mode signal voltage, no current will flow in either the collector resistors or in the emitters. Remember, a current is established when charges flow in a start-stop motion with a drift superimposed from a point of higher potential to a point of lower potential. We have connected the conductors in the circuit, namely the wires, resistors and transistors or semiconductors, in series beginning the terminal plus VCC and returned it to the same point. At switch on, a few charges may jostle around to establish potential conditions and the circuit will have reached static equilibrium. There will be no current if the signal voltages are zero and the output voltage at the collectors of the two transistors will remain at plus VCC. We had noted that when a full common mode voltage is applied to a transmission line with a terminating impedance, which may also be a shorted line, no currents flow in the source and load because there is no potential difference, being a common mode voltage, across them. A similarity in topology of the shorted line and the circuit of scheme 1 can be identified. Thus, no current will be produced in the transistors when the input is a common mode voltage. However, there should be a quiescent current to establish an operating point for the transistors in their active region, and a path for the emitter current to a negative power supply can be provided. This we shall discuss in the modification of scheme 1 in the video part 2 of 2.